Okay, as promised, we need to look at the complexity of this algorithm, and there's a lot to say about it. Um, there's more to say about like what follows from analyzing the complexity. Analyzing the complexity is kind of a simple process. Um, so I'm going to go ahead, I'll put it over here. Analyzing complexity. Okay, so let's think about how much time this took. So how long, well, let's go ahead and say this. Suppose machine M operates in time f of n. Okay, so let's think about. So first thing, observe this. So first, I'm going to type. A lot of this is the word, so I'm going to type some of it. First, observe that in f of n steps, none of the strings of m uh, can have more than f of n non-blank cells. This is an observation that I haven't made yet, but it's kind of important, which is that um, in f of n steps, you can only fill in f of n blanks, right? There's no way to use more than f of n space, or sorry, there's no way to use more than f of n time in f of n steps. And so there's a kind of a more general fact that I should probably, what the heck? I hate this program. Please, again, if you're watching this, if you have a better idea of a program to use, please let me know. Um, General observation, I'll probably have to write this down again later when we're looking more directly at the complexity classes, which is that for any f of n, it's always the case that time of f of n is a subset of space of f of n. That's just always the fact. The time classes are always contained inside of their space counterparts. Why? I can't, it's what I said before, I can't fill in more than f of n cells in f of n time. Now that's an obvious fact to state for Turing machines, um, but it seems kind of deep when you connect it to like actual computers, right? That the space classes are kind of bigger than the time classes in general. If we didn't have a model as rigorous and kind of simplistic at the same time as a Turing machine, this would not be at all obvious. But for a Turing machine, this is trivial, and it says something deep about the nature of computation in general, because Turing machines do stand in for any computer, your computer at home, just as much. So this is just a general fact about computation. Time is kind of a finer thing than space. It's a more refined quantity. And we'll talk more about that later. We'll talk more about the relationship between time and space. There's a lot to say there. But in any case, this is the same observation. In f of n steps, I can't have more than f of n non-blank cells per tape. I should have said that. Per tape. So how many tapes do I have? Um, and I'm talking about the original machine, right? And so there's k tapes. And so what does that translate to in our simulation? Um, well, how many tapes do I have? I have k of them. Each of them is at most f of n length. And so thus, the total length of m primes of the single string, the single tape of m prime, the simulating machine, is at worst length k times f of n plus 1 plus 2. So if you think about that, right? Each of these tapes, let's go ahead and zoom out a little bit. Right, each of these is length at most f of n. And so there's kf of n of them. So if I combine them all together, it's kf of n. But then I've also got these two guys. I've got this triangle and this triangle. That's the plus 2 at the end. And then I've also got this guy here, which is not there for any of the other ones. I've got this guy, this guy. These triangles facing left, I've got k of those. So I've got k of those. That's this one here. So if you multiply this across, you get k more of the left-facing prime triangles, and then you've got these two triangles surrounding everything, and then you've got f of n total. So this is the worst possible length. It's not even going to be this. It can't be this, but it's a bound. It's an upper bound. And the important thing to note about this is that it's O of f of n still, right? This is just a constant multiple. This is just these are just constant things added. It's still O of f of n. So the worst case length of a tape is O of f of n. That's important to note. Simulating. So what are we going to do with this, right? We have this O of f of n long tape, and what we're going to do is we're going to traverse this length. So for any one step of m, we are going to traverse this length 6 times, right? Forward, backward, forward, backward, forward, backward. One pass in order to read the input, one pass in order to write the input, and then another pass to make space whenever we need to make space. But again, this still isn't actually that bad, right? Because this basically means it's 6k f of n plus 1 plus 2. That's how many steps that takes, right? So that's gonna plus some stuff, right? We could, there's like 2 steps if I need to replace a symbol, but more or less approximately this, which is approximately O of f of n. And then there's one last thing to check, which is that, again, we're thinking about worst case here. So on third pass, and by third pass I mean like the second to last time we're traversing the length, we need to in the worst case, we will need to make space. That is, run the space creating subroutine k times. Right. That worst case is that I need to make the space at every single one of these guys, and we'll go ahead and be extra pessimistic, and we'll assume for simplicity that all of these. I don't need to do that. We need to make space k times. We're going to be moving along a chunk of the string that is length more or less, again, O of n. So, or O of f of n, because that's the length of the string that we need to do. So running subroutine requires O of length of string being moved. Right, it's an O of n algorithm. The thing we're operating on is not n, but the length of the string being moved, which is this. And so we'll take time. So the time required just to make the space each time is going to be k of these, k O of f of n. Right, I need to move a length of string. I need to move a string of length f of n. That's going to take O of f of n, and I need to do that k times. But of course, this k doesn't do anything. It's still O of f of n. It's a constant multiple. So total. So in total, the simulation of a single step of m is at worst going to be time 2 O of, well, really, it's kind of like, I'll just write it out, 6k, f of n plus 1 plus 2, and then plus the k of the O of f of n's that's required to make the space. But if you add all this up, look, it's just f of n, right? This is all still O of f of n. So we said a lot of words, but for very little. basically in order to simulate a single step of this machine M, it's going to take at worst a number of steps that's equivalent to the number of steps that M needs to take total. Thus, we need to simulate f of n steps, each taking time O of f of n. And so I need to do f of n steps, each of which takes time O of f of n. And so that is m f of n times f of n. What is happening with my mouse? Okay, so m prime operates in time O of f of n times f of n, which is, of course, O of f of n squared. Non-trivial. This is not O of f of n. This is the first time that we've encountered in our robustness facts, everything has been the same time, same space. But now we have a simulation that seems to be slower in a legitimate way that we'll have to talk about. One more thing before I get to that, though. Space complexity. Again, if M operates in space, G of n, then by this, because of the fact, then since time f of n is a subset of space G of n, remember that's what I said above. Oops, that's a capital G, that shouldn't be the case. So since time f of n is always a subset of space G of n, I know that, and m prime, I noted, right, the worst case length of this string is going to be O of f of n. So m prime uses space O of f of n. So m prime uses space O of g of n, right? Because f of n is an element of O of f of n, but it's also an element of O of g of n. My mouse is really glitching out. Okay, there we go. So no space loss. So no loss of space efficiency. Okay, so we have our time to time and space loss. If I want to go from a k-string Turing machine to a single string Turing machine, there's going to be a quadratic loss of efficiency. I should write that. So conclusion, there's several things to say. Extra strings, going from a k-string machine to a one-string machine requires a quadratic, which requires a maybe, we don't know yet, quadratic efficiency loss, time efficiency loss, but no space efficiency loss. Alternative conclusion, we can kind of say this in reverse, and that's when it gets interesting. An alternative conclusion we can make is that, it seems like extra strings then might provide some non-trivial speedup of some problems. But it's limited. But it's limited to, at best, quadratic speedup. So it's better. It could be better. I'm going to show you why it's better. It's better. It's objectively better, assuming that our simulation is optimal, which I'll demonstrate in a second, or I'll justify. But it's better, but it's very limited. Parallelism might and I'll show will provide some speed up, but it's at best kind of a square root speed up. So like at best, um, you know, square root of original time, which we'll see in the grand scheme of things is really not that great. It's not enough to really make any big changes to uh, the theory. But let's talk about this. So is this so this conclusion is true. This conclusion is only true provided our simulation is optimal. Is it? Let's talk about that. Is it optimal? How could I possibly know if this is optimal? How could I possibly know if there's a better, how do I know that there isn't a better algorithm that can do this process that I described? It's very rare that you can do that. However, in this case, you can prove that you can do that. And the key to proving that, believe it or not, involves our old friend, the palindrome problem. This was the first example we did, remember? I didn't do this for no reason, and you'll see that these problems, I will never show you a problem for no reason. All of these problems have some special importance. The palindrome problem can be used to actually prove that the simulation I just did is optimal. How the hell could that happen? Recall we made a one-string Turing machine, one-tape Turing machine, which decided PAL in time O of n squared. If you go back and you look at that algorithm, you'll see that it operates in time O of n squared. We also described, we didn't make it explicitly, but we described a two-string Turing machine, which decided PAL in time O of n. So we have two algorithms. We have two Turing machines that compute PAL. One was a single tape Turing machine that did O of n squared time, and the other one seemed like a big improvement. We had an O of n time. And there's a theorem that I've never actually gone through the proof of myself, but I could. I should probably. Um, so we have this theorem about the palindrome problem. Let M be a one tape Turing machine which decides PAL. Then it's been proven that M operates in time at best, I'm just going to write the symbols, at best n squared. Remember, O of n squared means worst case n squared. It works at a time less than or equal to this. This is the big omega notation. It means it works in time greater than or equal to this. So no matter what, it has to take time at least O of n squared is basically what this means. At best, at best. Thus, our Turing machine for PAL was optimal, meaning that it's a distinct improvement to go from a two-string Turing machine to a one-string Turing machine, or one string to two-string. This improvement that we got here was non-trivial. This was improvement that could only be gotten from adding more strings. So, thus, oh my, what is up with my mouse? Okay, there we go. Thus, if we let time k of f of n, we'll just kind of define this weird thing specifically, denote problems decidable by k tape machines in time f of n, then what we basically said by this theorem is that the PAL problem is an element of time 2 of n, but PAL is not in time 1 of n. And therefore, this class here is a strictly proper class compared to this. It's strictly contained. So these are not the same, definitively. So time f of n can be different depending on number of strings. But it won't be better. It won't be worse in a way that really like changes much. But this doesn't really matter much. Why? Because the main class that we're going to be concerned with um, is going to be P. And recall P is the union from k equals 0 to infinity of time n to the k. This is going to take, this is the main like efficiency class that we're going to be concerned with. And it's going to be the class of, it's going to be what we regard as the class of problems that are efficiently computable, that can be done efficiently. And since this contains all of these classes, um, this is the same regardless of how many strings the model uses. It's the same. This is still the same regardless of how many strings the model uses because, you know, if because for any k, we have that time of n to the k is always and time of n to the 2k are always both in time, are both contained. So the speed up doesn't really matter from the perspective of this big class P. And since this is going to be the main class we're concerned about uh, in terms of time and space complexity, the small amount of speed up that you get from multi-string machines and alternating between how many strings you're using will not affect what we're talking about. So in other words, the time classes are not the same depending on the number of strings we care about, but the big classes we care about are. P is still the same regardless of how many symbols my alphabet is using or what the alphabet is. It's the same regardless of how many strings my machine uses. It's the same regardless of whether I'm talking about one tape or two tape machines or unidirectional or bidirectional machines. It's the same no matter what. And I think through showing you these 4 robustness facts, I've probably at this point made you pretty confident that I could keep going and I would just be saying the same thing over and over again. There's other models, there's other kind of edits I could do to my Turing machine model to make it conceivably more powerful, and you would see every time that it just doesn't seem to matter. P stays the same no matter what. And so, this is kind of step 1 towards convincing you of a bigger, more philosophically loaded fact, which is the Church-Turing thesis, which is the fact that the model of computation just does not matter. But I think that'll be a topic to talk about in another video. So in the next video, we will put all of this stuff together that we've been talking about and build a universal Turing machine, which is essentially it's a computer in the sense that you typically think of a computer.